Hi, in this video we'll be talking about an application idea. So let's just get into the problem statement. You are given an array ARR with n zeros initially. You are also given a fixed R that will be a common GP ratio for all the queries. So we have some queries and R, small r will be the common GP ratio. Now find the array after q queries of the form plus ALR. So you need to do some updates, and there is ALR, that is add the GP with the first term A and common ratio R to the range L to R. So range L to R is given and the first term A is given to you, and the R for all the queries is common and is fixed and is given initially to you. Okay, so basically you add A to L, A times R to L plus 1, A times R square to L plus 2, and so on up to the last term where you add A times R to the power R minus L, right? So after performing all the queries, you will get the answer, the A array as some values. You need to print the final array modulo 10 to the power 9 plus 7. So let's just quickly look at the examples of the given statement. So we have plus 115, right? So this adds to the range 1 to 5. So if we quickly index the array, let's say 0, 1, 2, 3, 4, 5. Okay, so if we index the array, so there is this GP of starting value 1 and the common ratio 2, right? So the GP that we are talking about is 1, 2, 4, 8, 16, so on, right? So common ratio is 2, so you keep on multiplying with 2 every time, and that's the GP. And we need the first 5 term because we need to add it in the range 1 to 5, right? So we add that to the first 5 values in the range 1 to 5, and that's just 1, 2, 4, 8, 16, right? Then there is this second query where you have to add in the range 3 to 4, that is this range, and you have the starting value 2 and the common ratio 2 as well. So the value that you will need to add is 2, because that's the first term, then 2 times 2, 4, right? That's the second term, and that's all. Like, you need to add only in the range 3 to 4. So if we quickly consolidate all the values, like this cell will be sum of this plus this, so this is the second query array, contribution array. So this would be 1, 2, 6, that is sum of these two values, 12, and then 16, right? So this is the final array, and this is 0, obviously, like empty things are 0. So we need to build this final array. So in case you were given this queries to be processed one by one, you could have just brute forced. Okay, so if we brute force over the queries, we can just loop over from the given L to R and just add the GP. We can maintain the A, and every time we increase our loop, we multiply it with R when we loop from L to R, and we can add the correct values to the cells. And for each of the query, in that case, we would need order n, and in total it will take q times order n, that is order q times n, right? That's the total time taken, and that will be your final value. Now how do we do it better than q times n? So a general strategy for these type of problems could be, like, first of all trying to identify what is the general term that you have, and then try to decompose it. So that's what we have been doing till now, right? So you have this ALR given to you, right, and the common ratio R is given to you. So what is the general term that is being added to the ith index in the L to R range? So that is this A times R to the power I minus L, right? So if you put L over here, this becomes 0 and this becomes 1, so that's A, right? The first term gets A, and then next, so on, it keeps increasing by R one by one, and then the last term, if you put in R, that gets R minus L, right? And if you see, the original statement also had R to the power L minus R minus L, right? So that's what we are getting over here, and this addition happens in the range L to R. Now, can we decompose this given sum into two parts somehow? It turns out no, we cannot. So to decompose it into two independent parts, there is this R to the power I that's there. However, R to the power I is multiplied with A, so that's one part. we can handle that somehow if we had to, but again there is this difficulty that this is being divided by r to the power l, and this r to the power l changes with every index. So r to the power I is fixed, but r to the power l changes with with the queries, and r to the power I changes with index. So r to the power I is changing with index, r to the power l is changing by queries, and there is a division relation, and you need to get a summation. So you cannot distribute it across all the queries because r to the power l won't be constant across all the queries, right? So we cannot separate this sum out. So there's a big problem over here that we cannot separate the sum, and we cannot directly just use some decomposition into different arrays and then use the technique. So then how do we do this? So let's try to tweak the idea of prefix sum a bit. So let's say you're given an array A and you need to find the prefix sum of this array, but now we change the statement of prefix sum a bit. That initially if we had to build the prefix sum in place, we use this loop that we loop from 1 to n, and for each index I we had to add ARR of I minus 1, right? But now we, instead of adding ARR of I minus 1, we multiply it with R as well. So what do we get when we transform this? So this this is 0, this would get transformed into A itself, right? So this is A initially, and then you add ARR of I minus 1 times R, right? This is ARR of I minus 1, that is 0. Then when you come to this is 0, and then you add ARR of I minus 1 times R, so that is this times R, so that is AR. Then you add this times AR, so that is that AR square. Then you multiply this with R and add over here, so that's AR cube, AR4, right? So if you notice properly, just doing this loop over here is actually adding a GP with a starting index A and a common difference R, right? So that's what is written over here, that if you use this transformation, we are actually getting a GP contribution into the array by using this contribution, right? So that's what we are going to use in solving the problem. So initially if you had to add the GP of A13, so that is A square, AR square, so if that had to be added in the range 1 to 3, this would be the answer, right? So what we can do is that we can convert this query into adding at two places, that is A over here and minus AR cube over here. Now what are you doing over here? So that would be clear once we do the next step of the idea, that is this transformation that we talked about. Okay, this is the transformation that we talked about. So we know that this transformation, when it starts processing, it starts giving the contribution of this A as a GP over here, right? So the steps of the transformation for the first three values would remain same. So that this would come out to be AR, this would come out to be AR square. Now when we come to this is initially minus AR cube, right? Because we added these value over here, and then it gets added with ARR of I minus 1 times R. So you multiply it with R and add it to this, but it's already initially this. So AR cube minus AR cube, that becomes 0. And then once this is 0, you multiply it with R and add to this is 0, right? So this is happening in place, but this is what the initial value stores, right? So if you add A over here and subtract AR cube over here and then use this transformation, you are actually getting a GP contribution in a sub range, right? So the final idea is that whenever you get a ALR, that is contribution of the GP starting with A and the range L to R, you just add A to the range to the index L, and you subtract A times R to the power capital R minus L plus 1, that is the last cell value over here. So in this value over here, we added A to the 1, right? That is your L, and to R plus 1, that is 3 plus 1, 4, we subtracted A times R to the power 3 minus 1 plus 1, that is 3, right? So we subtracted over here, and in fact after transforming this using this, we were getting the correct answer. Now to get answer for a lot of queries, for all the queries, we first of all add these two values. Okay, for every query there will be two values to add, right? So for every query you have a range, so for that range you add correspondingly A and AR to the power whatever the value over here. So you, for all of the query, you do this thing over here, this algorithm, and you just change two places, add and subtract at two places, and finally run this transformation. Now why is this working even with multiple queries? Because for all of the queries, the contribution works separately in this loop, because R for all of them is same. So irrespective of which query it came from, this multiply with R will process it as if the queries are independent. Okay, so this is why this is working. Even if you first of all do all the queries and add the contributions over here in this part over here, like for every query you add two values and using this expression over here, and then you just build it using this transformation, you get a correct value. Okay, so what is the time complexity of this? So for every query you will need to add two values, right? And these are these two values. So adding this would take order 1. So if you had to find this R to the power capital R minus L plus 1, you had to use a order log in binary exponentiation, because they are given a modulo, right? So calculating R to the power something takes a need for binary exponentiation. However, we know that the range of the subarray that is given to us is never more than n, right? Like it cannot exceed the array size. So this value can up to go from 1, or let's say 0, because if L is equal to R, it is equal to 1. Okay, so this will always be greater than or equal to 1, and from 1 you need to go up to the value n, right? That's the maximum value, because you won't add to n plus 1 value, right? If this is the last cell, you don't, if R is the last cell, you don't add this value. So this can at most be n. So you can process all the values of R to the power 0, R to the power 1, R to the power 2, right? So you can save something called R pow array, which ith index of that stores R to the power I, and you can build this very easily, because R pow of I is equal to R times R pow of I minus 1. So you can build this array using a loop initially before all the computations start, and then for each of them you need to add these two values, and you can get this part in order 1. So this takes order 1 and this takes order 1. So in all, every query contribution in this will take order 1 to add to the contribution, and there are q such queries. So this part in total will take order q, right? Order q times order 1. So after you are done this, you just need to run this loop over here, that is this transformation of adding the GP part to for every cell. So if you do this transformation, this takes order n, right? This has a complexity of order n, this is order n, and you get the final array. So in total, the time complexity would be order q for every query addition of two values, and for the building this transformation we need order n. So the time complexity would be order q plus n, right, for this whole idea. So that's all for this idea. Thank you, and see you in the next video.